Morning, let's begin. This is lecture number 7, and a quick recap of what we have covered in the last lecture would be helpful for us. In the last lecture, we talked about antennas a little bit from the system's perspective, the usefulness of an isotropic antenna. One of the things that characterizes is the scale factors, which we represent as the area of an isotropic antenna. Again, it's a conceptual term. Basically, it's something that is helpful for us in terms of the characterizing of the wireless link. So the area of an isotropic antenna, if we take it as a reference, lambda squared by 4 pi, lambda being the wavelength of the carrier frequency, then we derive two very important expressions. One was the representation of the transmission equation, the transmitted power minus the path loss being the received signal power. Again, this is an equation that would be represented in dB, and I'm sure you're comfortable with that way of looking at it, because again, intuitively, when you look at it as path transmitted power minus path loss, that gives you the total power that is received. So if we characterize it in this fashion, the path loss itself for free space propagation is 4 pi d by lambda squared. D is the distance between the transmitter and receiver. And this is what we used as our baseline, and that helps us characterize the transmission from the antenna to some point which we call as D break. We assume that the transmission is line of sight, so therefore a typical AWGN type of transmission can be assumed, n equal to 2, free space path loss. The only impairment will be AWGN. Then beyond that, there could be other impairments which cause the signal to attenuate more quickly. So therefore, we see so this is received signal power versus the distance. We see that initially it decays as a square law, and then eventually at a higher exponent. So this is some of the elements that we had discussed in the last class. We also made a few other observations that typically an antenna would be characterized in terms of its elevation angle theta and the azimuthal angle phi. Transmit and receive gains are the same. We are also interested in the pattern of radiation. We typically have for mobiles omnidirectional radiation. This is different from isotropic, which radiates in all directions. Omnidirectional is omnidirectional in the azimuthal plane. Then we also mentioned that base stations do not radiate in all 360 degrees. They radiate with a specific pattern. Once you have a pattern, then you can talk about a 3 dB bandwidth of the radiation pattern, and that more or less defines how which is the area where the radiation will be focused. So the equation that we have for us is very much dependent on the transmitted power. Now there's another aspect that I would like you to be very familiar with and be confident of using, because transmitted power is what comes out of your power amplifier. Okay. Now after the power amplifier, if you go back and look at the original diagrams or any of the diagrams of a base station, you will find that there is an antenna. The antenna typically gives you some gain. So that contributes to the effectiveness of the signal that you have transmitted. So PT times the gain of the antenna is actually what you will see going out into the air. So typically we define a quantity called EIRP, effective or equivalent isotropic radiated power, more commonly known as effective isotropic radiated power. So this is like saying, okay, if I compared this with an isotropic radiator, what would be the power of the radiator be? That basically tells you this is the maximum radiation that we can expect from this antenna. But we keep in mind that this antenna is going to radiate only in a particular direction. So this is a way of characterizing the maximum power output of the antenna. So PT times GT is a very useful quantity. Now in many cases, the antenna has to be connected to the power amplifier by means of cables. That will introduce some losses for you. So before you get to the antenna, there is some loss. So that also has to be accounted for in link budgets. They are called the feeder losses. It's L subscript F. You may wonder what is feeding what. It is the power amplifier feeding the antenna, the cable that is feeding it, and there are losses in those. So that will have to be taken out. So the effective isotropic radiated power, which is what I would like you to keep in mind as we look at the link budget equation, will be the transmitted power that is coming out of the power amplifier times the gain, which will be a dB term. Antennas typically can have 20 dB gain or 15 dB gain depending upon the type of antenna you have designed. So that will be the GT. That's a positive factor, and then there is a negative factor which takes away from the calculation, which is the losses that we encounter in the system. So this is a quick summary of what we have discussed in the last class. We also started to talk about Molish chapter example 3.1. I hope you've had a chance to look at it. We will just quickly summarize the key factors from that example. But before that, let me just ask if there are any questions on the points that we have covered so far. Radiated power, EIRP, how the losses come into the picture, and how to characterize the breakpoint model. Okay, let's move on. So today's lecture will touch upon some aspects starting from the example. We'll also talk a little bit about fading margin. I want you to start thinking slightly differently about a fading model, and it is more in terms of a statistical quantity and not as a deterministic quantity, because fading is something that we cannot anticipate or we cannot tell ahead of time. It is a statistical impairment. Then as I mentioned yesterday, we'll talk a little bit about parabolic antennas. We don't use it on a handset or on a base station, but it is used for any type of microwave backhaul, which is also part of the cellular system. Then a comment about noise figure. Again, most of you are familiar with the understanding of noise figure, but I thought it would be helpful for us to also get an insight into the impact of noise figure on the system. I thought we will spend a few minutes on that. After that, we'll talk about noise limited systems, which is what we have been talking about. We basically are saying that there is no impairment. The only impairment is the losses that you encounter because of distance between the transmitter and receiver. That would be a noise limited system compared to a interference limited system, and that leads us into the cellular concept. So that is the rollout of the plan that we have. Reading assignment, we will definitely encourage you to look at Molish chapter 3, because that will complete the discussion that we have had so far. Please also read Rappaport chapter 2, because that introduces cellular concept. That's the next topic that we are touching upon. And as I mentioned, the cellular concept was introduced by a person by name MacDonald, and his original paper. And very rarely do we go back and read original papers. We don't go back and read Shannon's paper or Maxwell's paper, because it all happened years ago. But this happened quite recently in our lifetime, so it's good to go and see what was the thinking. How did he actually come up with the cellular concept? What was the problem that he was trying to solve? So I'm sure you'll enjoy reading it. Please do take the time to do that. It will be uploaded in Moodle. So let's begin with the discussion for today. And we will again answer any questions that come about. Okay, Molish chapter 3.1, example 3.1. I'm assuming that you had a chance to look at it, but let's take a quick look. The effective radiated power, isotropic radiated power, would be the power output from the transmitter. I think that was given to us as 45 dBm. There is a 10 dB antenna gain and a 5 dB feeder loss. So if you take all of that into account, the total EIRP is 50 dBm. That's our transmit side. Then we move over to the receive side. I'm sure you would have now, so basically we are trying to see how much path loss can we encounter. So this is transmitted power, this is received power, and what is the loss in between. So what is the receive level that I need to achieve? P min is given to us as minus 102 dBm, and we are told that we must account for a 12 dB fading margin. So which way do I go with the fading margin? The minimum receiver sensitivity is minus 102. I must make sure that I am coming at a signal level higher, 12 dB higher, in order for me to have the 12 dB margin. So if I add 12 dB, that means the minimum received signal power. It's not sensitivity, since your receiver will still receive at minus 102, but you have to design your system so that the minimum received power, including the margin, is at minus 90 dBm. Okay. So transmit minus receive is 140 dB. We are given that the D break is at 100 meters, so the path loss till D break is 72 dB. Notice how much of the energy you have already lost by the time you reach 100 meters, and the remaining distance accounts for the 68 dB. And given that n is equal to 3.5, I'm sure the calculation is straightforward. The distance comes out to be 8.8 kilometers. Okay, so EIRP, received signal power, receiver sensitivity, margin, path loss. What's in between is path loss. Okay. Any questions? Let me give you a way to visualize this, whatever we have been talking about, and I feel that this is a good way for us to, as engineers, to visualize the system. Okay, so here is a simplified way of visualizing the link budget. You have the transmitter, that you can assume that as the output will be the power amplifier that gives you a signal at a certain level. Then you have the cables that connect you to the antenna that will cause a drop in the power because that is the losses. Then the antenna gain, it may boost it back to its original power or maybe boost it even beyond what the original power was. That is the level at which you transmit. Okay. The other end, you have the thermal noise floor. Thermal noise floor plus the noise figure basically tells you where your noise power level is going to be located. Beyond that, you know that you must have a minimum signal to noise ratio. That is going to be your receiver sensitivity. Okay. Now, what else can happen on the receive side? You may have an antenna gain. Antenna gain will boost the antenna, boost the received signal strength, so that gives you a plus. There may be antenna connector losses, so you must account for that. That will cause an additional gap. Most of the time they cancel each other, and therefore you don't see much of a gain. However, as I told you yesterday, you may be holding the phone in a way that actually causes additional gain. So which means that there is an additional loss that you have to account for. Now, where is the margin coming in? Margin must come above receiver sensitivity. So basically, whatever is the, after you accounted for all the losses and the gains, if this is your receiver sensitivity, if you now want to include a margin, you say, okay, I cannot receive at this level, I must receive at a level slightly higher. That will be the acceptable received signal power. So the difference between the transmitted level and what you can accept with the margin is what we want to account what we account for as path loss. Now the path loss itself may have two components or three depending upon the model that you have used. We have used the simplest model where you have a single breakpoint which says line of sight or free space propagation up to D break, and then a higher path loss exponent post the D break. Okay, so visualize it as signal level, gain, loss, path loss, receive antenna gain, margin, and basically you sort of go up and down, but make sure that you've got moving in the right direction so that then you get your path loss calculations very correctly. Okay, any questions on why something is up, why it's down? I'm probably very intuitive, but if there was something that is not clear, that is K times T. Boltzmann's constant times T. So that basically sets your electronic noise floor. Right, if you multiply it by the bandwidth of the receiver, that tells you basically where you will have to set your threshold. Beyond that, there is noise that your receiver will add. That gives you that's the additional noise level. So from the what is the ambient noise for the particular receiver bandwidth that you're looking at, that gives you this threshold. Additional noise that your receiver electronics will add, that gives you the noise reference point, or noise power level in your receiver. Okay, so very important, but this is a calculation that we had done in the previous lecture. So basically it will be KTB, that will be this line, plus noise figure gives you Pn, that's this line. Okay, good. Now I want you to look at one more aspect. So here is a base station. You can see the base station here, and let's assume that you are a mobile that is moving in an arc with a certain distance d. Okay, very simple scenario, except that there is a building here. So when you are at the position A, you are able to see the base station quite clearly, so the received signal power is high. As you move to B, still slightly you start to see a drop. Then between B and C, there's a complete drop in signal level because there is a obstruction. And then when you go back towards D, the signal goes up. Okay? Very, very simple scenario. Now, this is what happens in reality as well, because there are obstructions, things that we don't necessarily know or plan for, those cause a degradation in the signal. So when I move from A to D, I cannot assume that the signal level is going to be what it's there at any one of those points. I have to say that there is a possibility of fluctuation of the signal level, and it is something that I have no control over. So what I have to say is there is a notion of an average signal level, okay, PR bar, average signal level. Okay. Now PR is a random variable which has got some distribution around PR bar. So again, we will introduce a notation a little bit more formally, but just sort of think about it. So the whole idea of our discussion is to say that I have a received signal power. Okay, or you can think of it as average path loss. Average signal power corresponds to average path loss as well. So average path loss is what I expect to see, but there is a statistical variation. And just for ease of visualization, I've shown it as a Gaussian distribution around that, and very often it actually fits a model that is close to Gaussian. So it's good for us to sort of use that as a baseline model. So if I design my system to have a path loss that is aligned with path loss bar, I've designed it for average path loss. And if I tell you that the definition of outage means the signal is not of acceptable quality. The outage scenario is when the signal goes below the received the acceptable quality. So outage basically means that the path loss that you are actually seeing is greater than path loss max, and you have designed path loss max for your scenario as PL bar. Okay, what's the probability of outage? Gaussian distribution. What is the probability of outage? Integrate from PL bar to infinity with respect to the whole thing. What is it? It's 1/2. So 50% of the time you are going to be in outage. Okay. Now that is not a acceptable situation. So what would you then rather do and say that, okay, no, I cannot design my system for 50% outage, I must design it for 90% outage or 95% outage. So 95% of the time the signal should be of acceptable quality. So which means that I cannot design the path loss to be PL bar, I must allow for a design that is greater than PL bar. So if I have moved my design point or the path loss allowed to this level, basically I've designed for this point, then the likelihood of outage decreases, because only if the path loss exceeds the green line I'm going to run into outage. So you can notice that the shaded region is what pushes me into outage. Okay. So the whole notion of margins is not some fixed number or some rule of thumb which somebody says, no, it's 10 dB, it's 20 dB. No, it is a statistical understanding of the channel and saying that, okay, the larger the margin, the better is going to be, or lower is going to be my probability of outage. So again, these are all interesting things for you to keep in mind, but I wanted you to start thinking about the whole notion of margins, the fading aspect, and how do you account for it. And of course, now keep in mind that this fading comes from two sources. One is shadowing, which you saw, the building type of obstruction, and then the other one is the multipath and the, constructive and destructive addition of those signals. So that is the second element that I want you to keep in mind. So why do we need fading margin? I would expect you to answer it in a very precise manner, refer to outage, it being a statistical quantity, and the way to handle the statistical aspect is to allow for margins, and at the end of the day what we can achieve is a percentage outage. You cannot guarantee 100%. Okay, I would also encourage you to look at Molish example 3.2. I will just give you the parameters again. I am sure you can refer to it. This is a problem which very similar to 3.1, but it's a very good practice. Let me just highlight the points that are important for us, and do take the time to. So the carrier frequency is given to us as 900 megahertz. Okay, very close to the previous case. The transmitter gain given as 8 dB. The receiver gain minus 2 dB. That means it's an antenna that's inside and you're holding it in a funny way, so the gain is minus 2. Okay. The feeder losses at the transmitter side we are given as 2 dB, and the noise figure of the receiver is given as 8 dB. Okay. We do need to understand the baud rate. So it is a system with a bandwidth of 25 kilohertz, which also tells me that my baud rate is 25 symbols per second. So the equivalent bandwidth that I need for my translation from EB by N naught to PS by PN, that is taken to be 25 kilohertz as well. Okay. I want to achieve a PS by PN of 18 dB. PS by PN of 18 dB. And we are told that asked to use a breakpoint model with a D break of 10 meters. Again, maybe just a quick comment on this. The previous example was 100 meters. Now you may wonder why do you take 10 meters? Is just to check whether we are doing the math correctly. No. When will you get 10 meters? Only line of sight? Urban areas, or you're mounting it in a campus environment without too much of a height of the antenna. So basically after 10 meters you are going to hit obstruction. When will you get 100 meters? In some rural area, or where you put the antenna on top of a very tall mast. So 100 meters it sees without any obstruction. So again, it is not just another exercise. There is a reason behind the points that are mentioned. Beyond the D break, we are asked to use a path loss exponent of 3.8 and introduce a fading margin of 10 dB. The question that is being asked is, what is the transmitted power, EIRP? That's the question. And usually this is a more important type of question that arises. Given all these scenarios, what is the received signal power, transmitted signal power? What I want to guarantee is the signal to noise ratio at the receiver, PS by PN. And I want to give a fading margin as well. So what should be my transmitted power? Okay. So again, keeping in mind that we are talking about EIRP, you can adjust the EIRP by increasing the gain of the antenna and reducing the power amplifier output, or it doesn't matter. Again, what we are asked here is only the EIRP. So that's enough to get a question.
So, we need a distance for the receiver.
Well, basically it says that I must achieve PS by PN of certain distance. Do I need a distance? Well, if you were told the transmitted power, you can calculate. You probably need the distance. That's a very good question. You do need the distance of the cell. It's there in the problem statement. So this is very good example for us to take a look at and solve. And if there are any questions, we will clarify it in the class. But I think once you get the basic feel for it, this should not be a problem at all. Okay, I want to spend a few minutes talking about parabolic antennas, again, as I mentioned, these are used in a number of applications in communications. So let me just take a minute to sort of get you excited about wireless, because this is, something very, very good for us. So as I mentioned earlier, the area of an isotropic antenna is lambda squared by 4 pi. And we always characterize the gain of an antenna in the following fashion. You take the gain of your own antenna that you have and compare it to the gain of an isotropic antenna. Okay? So basically it is AE, the equivalent area, that's what will be the area, what will be the effective received signal power or the gain of your antenna, divided by A ISO. This is like saying, what is your gain relative to the gain of a isotropic antenna. And if you were to express it in dB, you will also see dBi represented there, and that says it is dB with respect to an isotropic radiator. So typically the gain of an antenna will be 8 dB, or correctly speaking it should be 8 dBi. Okay, so the effective area of a parabolic antenna, the cross section is a circle. So the effective area of a parabolic antenna, so basically this is parabolic antenna, this would be pi d squared by 4, and if you remember, this is effective area, so the entire area does not contribute. So basically there's an efficiency factor that must be accounted for, and typically it is in the efficiency is in the 40% to 80% range, depending upon how smoothly you have done it, how perfectly you have made the parabolic reflector, all of that accounts for it. So if I now were to ask for the gain of a parabolic antenna, G of a parabolic antenna, this would be eta times pi d squared by 4 into 1 over lambda squared by 4 pi. Okay, so basically the effective area of a parabolic antenna divided by the area of an isotropic antenna. So this basically, I'm sorry?
What is 40 to 80%?
The eta. The efficiency of a parabolic reflector would be, any antenna is in that range. So the cross-sectional area times the efficiency of the antenna gives you the effectiveness of the antenna. So this is given by eta times pi d by lambda whole squared. Okay. So this is typically how you would characterize the gain of a parabolic antenna, and what I want to share with you is an example of a parabolic antenna, the largest parabolic antenna that we have built, and some amazing stuff that has happened with that. So when you get a chance, please do look up something known as the NASA Deep Space Network. NASA Deep Space Network consists of 3 antennas, and they are located in 3 different parts of the world, and one of the interesting elements that you would notice is the size of the antenna. Okay, so this is what the antenna looks like. One of the antennas looks like it's sitting in a desert, because doesn't want to have a minimum amount of interference from other sources. The diameter of this antenna is 70 meters. If you ever gone to the stadium and you look at 100-meter track from one end to the other, this is almost the size of that. So it's a huge antenna, and it weighs 2.7 million kilograms. 2.7, that's the dish, is what that's how much it weighs, because it's basically metal, and you can think of what it takes to build this type of an antenna in 1960s. Basically, this was when NASA was doing their deep space mission. They knew that they were going to launch spacecraft that will go into beyond out of their solar system. They needed to track it. So basically, they designed a 3 antenna system where 3 parts of the world, one in Spain, one in Australia, one in the US, and it's as a communications engineer, when you actually go and see, when you go and study these things, absolutely fascinated by what it can do. So let's just look at the specifications of this. It achieved an efficiency of 50%. When you design such a large parabolic dish, it cannot be a single sheet of metal. It is individual sheets of metal then that are stitched together. So of course you don't get a perfect finish. So this is about 50% is what? And the diameter is 70 meters. That's a huge antenna, and it can operate in a wide range of carrier frequencies. Basically, it was designed for 2 gigahertz to 4 gigahertz, and probably the record that it set was for a spacecraft called Pioneer 10. Pioneer 10. Look it up, very interesting. It's a spacecraft that went out of our solar system many years ago. But the last communication from Pioneer 10, by the way, Pioneer 10 had an 8-watt transmitter, just 8 watts. And the last communications was when Pioneer 10 was at a distance of 1.6 into 10 power 10 kilometers from ground station. And the Deep Space Network actually picked it up and decoded the signal. It's one of those things where you say, oh, this is absolutely amazing, because the 8 watts is lower than most of these bulbs. And just imagine that is the power at which you transmit from a distance of 10 power 10 kilometers and actually the space network. But the amazing thing about it is not that is one element of it. I want you to one more element of this one is the error correcting codes. Of course, it was able to achieve this because of the error correcting code. I'm sure you have studied forward error correction, right? And you have studied Reed-Solomon codes, very powerful codes. But the interesting thing is, when Pioneer 10 was launched, Reed-Solomon codes were not yet invented. So what did they do? After Reed-Solomon codes were invented and they were verified and they were proven to be the most powerful codes, from the ground station they actually programmed the microprocessor on board to do Reed-Solomon code. So in space, when it was outside, gone past Mars and Jupiter, they actually programmed it to do Reed-Solomon code. So then it switched over from convolutional codes that it was doing to Reed-Solomon codes, and then actually was able to communicate, and that's how the last communication was with ground. So again, wireless communications is about some absolutely fascinating stuff, and hopefully you get excited and read. But our things is a little bit less ambitious. We are 3 kilometers, 2 kilometers is what we want to communicate. Reed-Solomon is good, but convolutional codes is good as well. So I think it is, we come back to ground and start talking about terrestrial cellular. So but I thought it's always interesting for you to get a perspective that this is absolutely exciting stuff. You can do things which are, it looks like science fiction, but that's wireless communication. So let's move on to our understanding of noise figure, because this is also important, because it helps us keep the practical aspects in mind. Can you give me the definition of noise figure? What is noise figure as textbooks define it? Input SNR, thank you. So basically it is SNR at input. Let me just write it in short form, SNR input by SNR output. Now if this number is greater than 1, that automatically tells you that the output SNR is less than input SNR. So in other words, somehow your receiver has added to the noise that is already present in the system. Okay, so the total noise at a receiver, which I have understood it to be KTBF. Okay, K is the Boltzmann's constant, T is the ambient temperature, B is the bandwidth, and F is the noise figure. That's how you have calculated, and that's how we have done it. Now I want you to visualize this in a very interesting and novel manner. To split this as KTB, that is ambient noise, right? Ambient noise without the receiver. This is what's there if you were to look at the bandwidth that is present for you, plus KTBF minus 1. Okay, KTBF minus 1. So this is what is referred to as whatever is there in the ambient, this is what got additionally added because of your receiver. Okay. So this T times F minus 1 is a very important quantity because they call this as the effective temperature of your receiver, effective temperature. And this total KTB F minus 1 is the effective noise temperature of your receiver or the effective contribution of the noise. It's as if your receiver was operating not at ambient but at a slightly higher temperature, and you want to sort of account for that. So ambient noise plus this noise together is the effective total noise, and at the end of the day it's KTBF, so no confusions about that. But let's see if we can understand this a little bit better in terms of the figure on the left hand corner. So think of it as a simple amplifier. Amplifiers also add noise. So this whole issue of noise figure can be easily understood in the context of an amplifier. An amplifier with gain G, input signal power Si, input noise power Ni, and there is some additional noise which shows up at the output, which I call it as Na. Okay. What will be the total signal power at the output? Si times G. What's the total noise power at the output? G Ni plus Na. Na is the power noise power of the signal that's added at the other side. Okay. So let's write down the definition of SNR input by SNR at the output. SNR at input would be Si by Ni divided by SNR at output would be G times Si divided by G times Ni plus Na. Okay. Now do some simple juggling of the expression, factor out the G. This can be written as, I'll just change colors so it's easy for us to see, Si by Ni divided by Si by Ni plus Na divided by G. This has two important implications. If you wanted to reflect the noise of the amplifier to the input side, what should be the power level? It should be Na divided by G, because that would also get amplified by the amplifier. So this gives us a good way to visualizing it's there was already Ni power, Ni noise power present. Na by G also got added, and then together this thing got amplified, and that's how we got this expression. Okay. Now take it one more step. Basically factor out Ni on both sides. So let me use one more color, let me use green. So this can be written as Si by Ni. I'm going to factor out Ni, so then I get Si by Ni divided by 1 plus Na by G Ni. Okay. So Si by Ni will of course cancel. That gives me a very, very important result that the noise figure is 1 plus Na by G Ni, or Na by G is equal to F minus 1 times Ni. Okay, that's a very, very useful way to visualize. And again this F minus 1, why is the F minus 1 coming into the picture? Because one component comes from ambient, that's already present. Now what is newly getting added depends on F minus 1, but together the effect of the total noise is F. I can split it just for visualization in this fashion. Okay, everybody is clear on this aspect. Okay. So now we move to the realistic situation where you don't have just one amplifier, but you have several cascade of components which will give you the following aspect. So the first system, let us say, has got gain G1 with noise power N1, G2, N2, G3, N3. So the way to visualize this scenario is I want to look at the total noise total noise. So total noise will be Ni, that is what is coming in at the input. First stage, if I want to reflect it to the input side, it will be N1 by G1, then it will be N2 by G1 G2 plus N3 by G1 G2 G3, okay, and so on, plus dot dot dot. Okay, again, if you reflect all of them to the input side. Okay, what is N1 by G1? It will be F1 minus 1, correct, times Ni. What will N2 by G2 be? It will be F2 minus 1 times Ni. N3 by G3 will be F3 minus 1 times Ni. Okay. So now if I were to rewrite the equation and pull out the Ni factor and then look at the effective noise, this is what we get, and this is a famous equation that you would have been familiar with, which says that the overall noise figure when I have a cascade is equal to F1. That means if there was no other components, F1, that is traditionally how we have understood receivers to function. But if there are cascaded terms, the second one will contribute F2 minus 1 divided by G1, F3 minus 1 by G1 G2 dot dot dot. So the noise, the interpretation of this expression is F1 I can't do anything about. F1 is basically the, if I did not have a cascaded system, the noise figure of my front end becomes the noise figure of my receiver. However, if I have a cascaded system, the noise added by the subsequent sections are downgraded to some extent by the gain of the preceding terms. Why is that? Noise at a certain level. If the preceding stage has already amplified my signal by G1, it is like saying keeping G at the signal at the same level and suppressing the noise by G1. So second stage noise is suppressed by G1, third stage noise is suppressed by G1, G2 if you keep the input signal level at the same point. Okay. So this is a very, very useful visualization, and again this is for cascaded systems, and if you do have to work with it. So when you take a look at any practical receiver, the whole idea of this discussion was to make sure we come to this stage. You will see that there is an antenna, and this is the way we describe an RF filter. 3 lines representing the high frequency, the low frequency and the middle frequency. If I cancel out the high and low, what I am left with is a band pass filter. So this is basically a band pass filter because it allows the middle frequencies to pass. It does not tell us what those middle frequencies are, but it tells you that one minute you look at this, you know that it is a band pass filter. The first electronic stage that you will counter after the band pass will be a low noise amplifier. Okay? And the reason for that is because this is what is going to decide the overall noise figure of the system. All subsequent electronic components are going to be suppressed in terms of their noise contributions by the gain of the low noise amplifier. Okay. So the LNA is very, very crucial in our design. Maybe a simple example will give us a way to appreciate that. Let us look at case 1. Case 1, I have to design a receiver with 80 dB gain. G is equal to 80 dB. So I have to have a lot of gain stages to get the signal to the received level, and the noise figure that I have is 10 dB. Okay. So what will it have? What will it do? This is a receiver that will degrade whatever is my input noise signal to noise ratio by a factor of 10 dB. So again, now I have a case 2 scenario. Case 2, I'm going to design it as a cascaded system. I'm going to have G1 very, very modest, 10 dB gain only, but it's a very low noise amplifier. I have gotten it to be a noise figure of 3 dB, followed by a second stage where I have a gain of 70 dB. I have to get overall gain 80 dB, so I have gotten a second stage of 70 dB, and this is less like the previous one. noise figure of 10 dB. At a glance, they don't look too different. 80 dB, 80 dB. First one 10 dB noise figure, this one you may say, oh, first stage, okay, you did a very good design, but second stage, look, you messed it up by putting a 10 dB noise figure amplifier stage or stage. So which means that, well, wait a minute, this is a cascaded system, so therefore the effectiveness or the effective noise figure is 3 dB corresponds to 2 plus 10 dB corresponds to 10, so it's 10 minus 1 divided by 10. The gain of the first stage is 10. So the effective effective or I think we use the term overall is 2.9. Much different from the earlier case, this corresponds to 4.6 dB. So without doing much, you have actually improved your performance of your receiver by 5 dB, and 5 dB is worth a lot in cellular systems. Those of you who are doing research know that even 1 dB makes a huge difference. So that is a important element that I want you to keep in mind. Okay. The next point that I wanted you to think, we have talked about fading margin. I want you to quickly introduce the concept of a noise limited system. So all that we have learnt so far, I want you to put it together in a single framework. So the framework is that we do have a certain noise floor over which we don't have too much control over. Okay, so notice that basically the red line tells us the noise floor. All the clever designs that we have done, cascaded systems, and all of that together tells us this is where my noise level is. Basically it's KTB, KTBF. On top of that, you must maintain a minimum signal to noise ratio, SNR min. That tells us that you have to have the received signal level at least at the blue line. On top of that, if you want to introduce a margin, that blue line will shift a little further up, assuming that you know what the impact is. So that is where you say that that's now the received signal power, starting from the close to the base station or to the mobile, or from the mobile to the base station, starts off at a high level and decays with some exponent. Again, I have just shown it as a single line, it may have a break point, doesn't matter, it decays with distance with some exponent. Now at some point this green line is going to cross over the blue line. That means your received signal power is going to be below what you consider as the minimum received signal power for your system. It is receiver sensitivity. If there are no margins, it will be higher if there are margins, but at some point it's going to cross the blue line, and that is going to be the maximum range that you can cover with your system with a given amount of reliability. This is a picture of all that we have talked about so far. Okay, is this picture clear? Anything that is not clear about this picture? Because if this picture is clear, then we are ready to talk about the next concept, which says that if I have another base station that is using the same frequency, that's the purple line. Now the purple line is going to decay as distance from this base station is going to, and we'll count the distance from this base station from the right side, and you find that at some point this purple baseline will also cut the blue line. Okay, but probably long before it cut the blue line, it actually intersected the green line. Okay, now that point of intersection between the green line and the purple line, what does that tell you? If I am a mobile sitting at that distance from, I am equidistant from both base stations, assuming both are transmitting with the same power level, I am receiving this base station signal with the same power as this base station. This is desired signal, this is interfering. I have no idea what this base station is talking about. What is my signal to impairment ratio? 1 or 0 dB. Almost none of our communication systems work at that level. So which means that I cannot even come as far as the intersection point. I have to stop at that point where my green line is, it has to be only at a sufficiently high level above the purple line. The minute it gets less no communications will not work. So whatever was your that minimum signal to noise ratio now has to be defined in terms of signal to interference plus noise ratio. SINR is signal to interference plus noise. You don't care whether it's interference or noise or both, but the effective impairment, the denominator term with respect to the numerator term has to be at a certain level. So this tells me that what used to be D max previously now may be much smaller. Okay. This is an interference limited system compared to a noise limited system. So when I start using multiple base stations with the same frequency, I run into an interference limited scenario. Okay. So what is an interference limited scenario? When does it arise? That comes from McDonald's concept. That's called the cellular concept as he envisioned it. It's a paper that was written in 1979. It will be uploaded in Moodle. Take a look at it. We'll discuss it in detail in class. It's absolutely, from an engineering perspective, it's a brilliant piece of work. Very elegant, very simple. And you say, well, I would have thought about it. That's good. That's the way you should people should write papers and come up with new concepts. Thank you.